So today we'll continue with crystal field theory. We've already talked about how the crystal field theory, how it splits into octahedra and tetrahedra, into octahedra. We left out the tetrahedra because you do that maybe when you get to 400 level. So we have looked at the splitting where we have the T2G and the EG. Where we say the T2G is triply degenerate and the EG is doubly degenerate because the EG now has two orbitals that have the same level, while the T2G now has three orbitals that has the same level. And I told you there is no center of symmetry. That is why we have the G, no center of symmetry. Now we are going to look at how to calculate. We are going to look at how to calculate the crystal field stabilization energy. How do we know if it's stable based on the calculation we are going to do? So we have the crystal field stabilization energy. Which is actually a measure of the net energy of occupation of the d orbital relative to their mean energy. So what that actually means that for us to calculate the crystal field stabilization energy, we're actually going to get the net energy of the EG and the T2G. So I will know that the T2G is minus 0.4 or what we call minus 2/5 delta O, while our T2G, while our EG, sorry, is plus 0.5 or plus 3/5 delta O. So it is actually the net addition of these two EG and the T2G that will give us the crystal field stabilization energy. So energy of T2G orbital is this and EG is this. So when we add both of them, that is actually what gives us the crystal field stabilization energy. You understand it more by the time we start doing the calculations. See? This thing should not disturb me today, I beg. Okay. So before we go on to calculation, we first of all have to learn how to distribute the electrons. Let's say you have a manganese 2, which automatically comes up to your 3d5. How are we going to distribute the electrons in your T2G and your EG orbitals? So the distribution of electrons in these d orbitals under the octahedral field, we actually apply the building up principle. We already know the building up principle, whereby the first one says that maximum of 2 electrons in an orbital will be placed if more than one degenerate orbital is available. What it means is that if you have more than one degenerate orbital, you are going to first of all apply the Pauling exclusion principle, where a maximum of 2 electrons in an orbital will be placed if you have more than one degenerate orbital. Then aside, of course, first of all, we are going to fill in singly before pairing. That is, electrons are filled singly before pairing. So you add 1, 1, 1 before you start pairing. And of course, we know that for each orbital, the maximum number of electrons is 2. But they will first of all enter singly before pairing. Also, electrons occupy separate orbitals and do so with parallel spins. So we know that this is, let me see if I can. Something, okay. So what we mean that, let's say you have this 1, 2, 3, 1, 2. These are T2G and this is our EG. So we enter singly before pairing. And when they are pairing, of course, we expect it to be the opposite spin. So this is actually what I'm trying to explain. So electrons occupy separate orbitals and do so with parallel spins. They are filled singly before pairing. And we have a maximum of 2 electrons in an orbital. So that is actually the distribution of electrons using the building up principle. I don't know how we are having this today. Okay. So now we look at some examples. Sorry, based on what I've explained. Using your titanium-2 and your vanadium-2 as examples. Our titanium is 3d24s2. So automatically our titanium-2 becomes 3d2 because 2 electrons will be lost from the s orbital. So that gives us 3d2. So how do we feel? Of course, you start feeling from the lower energy before the higher energy, but that will depend on the kind of ligand, which I'm going to explain later, because the kind of ligand will tell us if you are going to have a small delta O splitting or a large delta O splitting. Let me show you what I mean by that. Sorry. Okay. So I'm going to draw 2 scenarios. 1, 2, 3, 1, 2. And we'll have another one. 1, 2, 3, 1, 2. So if you have a large delta O splitting, what it means is that this distance here is so high that all the electrons, when they are coming in, they'll want to be at this low energy level. Mind you, these are T2G and this is our EG. T2G and this is our EG. But if you have a small delta O, what it means is that as the electrons are coming in, because this delta O because this delta O is small, the electrons can easily enter and go to a higher energy level.
Why?
Please mute yourself before I send you out of this class. So this is actually what happens. Is you have a large delta O, then the electrons will decide to be at the low energy level because they need more energy to bypass this delta O to go to the high energy level. But if the delta O splitting is small, then they can easily jump to the high energy level, which is your EG. And this delta O, whether it's going to be small or large, will depend on the ligand. If it's a strong field ligand or if it's a weak field ligand. Who are those people talking? By the time I send you out of this class, that is when you understand. So that is actually what I've tried. So for titanium 2 plus, vanadium 3, vanadium 2, we see that whether it's a strong field ligand, whether your delta O is small or large, is going to have the same configuration, because you can only have a different configuration by the time you start getting up to D4. Because for D4, you are going to have about 2 scenarios. Either the 4 of them will enter here, or 3 will enter here and 1 will enter here. That is what will not, so it's the ligand, the type of ligand that will not determine that type of configuration. But for your titanium 2, which is a 3D2, this is the only kind of configuration you can have. You can't have any other scenario. For your vanadium 2, which is your 3D3, this is the only kind of configuration you can have. You cannot have 1, 1, and you not have 1 here. It doesn't work because of the build-up principle. You have to enter singly before you start pairing or before you start going to a higher energy level. So for D1, D2, D3, you are going to have the same configuration because all of them are all going to be at the T2G level. Now, how do we calculate? So for the crystal field stabilization energy, we have only 2 electrons. So we have 2 times our T2G. We already know that is 0.4 or 2 over 5, which will give you 0.8 delta O. For your vanadium 2, which is your 3D3, we all have only 3 electrons, so it's going to be 3 times 0.4. So if you will see when we have at your EG. So for these complexes, only one type of configuration is possible, including your D1 complex, just as I've explained. For your D1, D2, and D3, you're going to have only one kind of configuration. And we say that this type of configuration are what we call high spin complexes. They are called high spin complexes because they are not paired. They are all high spin complexes. Now, for your D4, as I said, we are going to have 2 types of configuration. Let me explain what I mean. I think you understand more when I use the blackboard. So for our D4, let's see what do we have for our D4? 1, 2, 3, 1, 2. So for D4, we say we are going to have 2 scenarios for our D4. So we are going to have a situation where the delta O is large and a situation where the delta O is small. So for delta O that is large, we are going to have this, this, and this. Because for this electron to jump to this energy level, it requires more energy. So it will just decide to be at the low energy level. But for this, that the delta O is small, we have 1, 1. Because it's small, it can easily jump to a high energy level. So this is the scenario for your D4. If we were in class, I would have asked you to do for D5 and D6. So your D4, D5, D6 will always have the different scenario of having 2 scenarios when the delta O is small and when the delta O is large. Who is that one? So I'm trying to make you understand. That is why I'm using the blackboard. So this is actually what I've tried to explain. For D4, you have 2 scenarios where you have all these. So this is for the delta O being large, and this is for the delta O being small. So the electronic configuration automatically becomes T2G 4 EG 0 because there's no electron in the EG orbital. Why for this? You now have T2G 3 EG 1. Now for this scenario, a strong Coulombic repulsion is experienced, which is called pairing energy. That is for this. We have pairing energy because there's a pairing here. A strong Coulombic repulsion is experienced, which is called pairing energy. Of course, when there is pairing, there's going to be a repulsion because there are two electrons here. So you expect more repulsion here than here where they are all singly. Alternatively, the electrons may occupy one of the e orbitals such that the pairing energy is avoided as shown in B. So for this, of course, they are singly, so there's no pairing energy. But here, there will be more repulsion because there's already electrons that are paired here. Of course, when the electrons are paired, this is an electron, this is an electron, of course, we expect them to be repulsion. So this leads to a high orbital energy delta O. Placement of these electrons can result due to two types of field, which we call weak field or strong field. And I told you when we talk about weak field and strong field, we are actually looking at the kind of ligand. I gave you this petrochemical series for ligand, like your cyanide, your NO, your CO, all those are strong field ligand. And because they are strong field ligand, they are going to lead to a high delta O splitting. But the weak field ligand, because they are weak, so the splitting will not be much, so it will be small. So placement of electrons can result due to two types of field, weak field or strong field. Strong field has to do with strong field, that is what another name we call it is a strong field ligand, or weak field. When the field around the ligand is weak, then the splitting will be small. And when the splitting is small, all the electrons would prefer to be at the T2G level. But when this field is strong, then it will split very high. And when it splits very high, for the weak field ligand, you have electrons both at the T2G and the EG. That is if you have as from D4. But for the strong field ligand, because the delta O splitting is high, the splitting is very, very much. So the electrons will prefer to be at the low energy level because for them to jump to the high energy level, they need a very high energy. So for a weak field case, delta O is less than pairing. So that means the delta O splitting is large. So a lower energy is achieved if the upper orbital is occupied such that the electronic configuration is T2G3 EG1. That is this. So for us to have this, what it means is that the delta O has to be small. And when the delta O is small, so delta O is going to be larger than the pairing energy. This is where we have the pairing energy. So for a strong field case, delta O is greater than pairing energy. A lower energy is achieved by occupying only the lower orbital despite the cost of pairing. So despite the cost of pairing, because the delta O is large, they will prefer to pair than acquiring more energy to go to a higher energy level. So despite the cost of pairing, which is high, they will still prefer to pair because the delta O here is actually large. So delta O is greater than pairing energy. So we look at some other examples. Your chromium, this is your chromium 2 because our water here is a neutral ligand, so your chromium is chromium 2. Here, your chromium is also going to be chromium 2 because cyanide is -1 multiplied by 6, that is 6 minus 4. So our chromium here is also chromium 2. So both of them are both chromium 2. But we have, this is a strong field ligand and water is a weak field ligand. So what do we expect? So we are going to look at that. So let's go back to our blackboard and see what we expect. We already have the configuration, but you understand. Let me let you know. Okay, let's clear all this. So we have our chromium with water. And we have our chromium cyanide. 2 minus. So I told you both of them are both chromium 2, chromium 2. So what do we have here? So for this, we have 1, 2, 3, 1, 2. For this, we also have this 1, 2, 3, 1, 2.
Hello.
Yes, they can hear you. Yes.
It's -4 for the cyanide.
Oh, so, -4 where? Oh, sorry,
Yes.
dear. Sorry. You're right. Thank you. Thank you. Good. That shows you are following. I'm happy. So we said that this is a weak field ligand, isn't it? So what it means is that the splitting is going to be small. But this is a strong field ligand. So bam, it will split very large. Both of them are D4, isn't it? Am I correct? Both of them are D4. Because your chromium.
Yes, Mom.
Yes.
Good. Both of them are D4. So D4, D4. So what do you expect? This is a strong field ligand. So the splitting is small. So we have 1, 2, 3, 4. This one, the splitting is small, isn't it? So we have 1, 2, 3, and we have another one here. So the electronic configuration for this will now be T2G3 EG1. Why for this will now be T2G4 EG0. You see, we have the same chromium. Both of them are D4, but because of the kind of ligand, we are having different type of electronic configuration. Okay. So let's go back. I hope you are following. Are we following?
Yes, ma'am.
Yes, ma'am.
So that is why for this we have T2G4, so it's going to be EG0. Why for this we have T2G3 EG1. So the occupation of electrons in the orbitals T2G and EG depend on the ligand, just as I've told you. If it is a strong field or weak field ligand from the spectrochemical series. So you have to know ligands that are strong field ligand and ligands that are weak field ligand. That will tell you the kind of splitting, and that would not let us know how the electrons are going to enter into the T2G and the EG level. And this affects the delta O and the pairing energy. Now, we've looked at D1, D2, D3, and we said that they will have the same scenario because all the electrons will enter the T2G. Now, we have a different scenario for a D4, D5, D6, and D7. For these ones, we are going to have two scenarios of electrons, either all of them being in the T2G, or another scenario where we have some electrons in the T2G and the EG. And that will be for your D4, D5, D6, and D7. If you were in class, I would have asked you to do it. But now, even if I ask you to do it, I will not see it. I can just, let me just do for D. I've done for D4. Let me just do for D5. Then you now do for D6 and D7. Please try and do it. So let me do for D5. I've done for D4. We've seen the two scenarios. I'll do for D5 and I will do for D6. You do for D7. So for D5, we are going to have two scenarios. Let me do for D5 first, the two scenarios. I will do only D5. I won't do D6. You can try it out. T2G, EG, EG, T2G. So let's assume that this is a strong field and this is a weak field. So for strong field is high, so all of them are going to remain at the T2G level. So we are going to have this. For the weak field, so we are going to have all singly and they can now jump. So we have T2G5 EG0. While here we have T2G3 EG2. So these are the two scenarios for your D5. We also have two scenarios for our D6. So for our D6, we now have another one here. So we now have T2G6 EG0. Why for we are now for D6. So we now have 1, 2, 3, 4, 5, of course, 6. So we now have T2G4 EG2. So these are the two scenarios for D5 and D6. So you can try off D7. So you can try off D7. You can try off D7. So now for D8, we have D8, D9, D10. For this, whether strong field or weak field, we are actually going to have almost the same scenario. Let me tell you what I mean by that. Let's use D9. You will do D8. Oh, sorry. Let's look at D9. Let's look at D9. You do D8 and D10. You are going to have two scenarios, but whether strong field or weak field, we are going to have the same electronic configuration. This is a strong field and this is a weak field. So for D9, we have 1, 2, 3, because 3, 4, 5, 6, 7, 8, 9. This is for your strong field. You see, this one was completely filled for us because the energy here is high before we go here. Now for weak field, of course, they will jump immediately. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So whether it's a weak field ligand or it's a strong field ligand, we are going to have the same electronic configuration for your D8, D9, and D10. So you are going to try the D8 and D10 on your own to see if actually, whether strong field or weak field, we are going to have the same electronic configuration. So here we have T2G6 EG3. And here we also have T2G6 EG3, irrespective of whether it's a weak field or it's a strong field. So D1, D2, D3, all the electrons are in your T2G orbital, which I have told you. D8, D9, D10, all electrons occupy both T2G and EG orbitals. So they have the same electronic configuration for your D8, D9, and D10, irrespective of whether strong field or weak field. So there's no competition between delta O and their pairing, especially for your D1, D2, D3, D8, D9, D10. It's your D4, D5, D6, D7 that there's going to be competition. If all the electrons are going to pair first, or the electrons are going to go into the higher energy level. Because a strong field favors occupation of lower orbitals T2G, while weak field allows electrons to escape the pairing energy to occupy your EG orbital. So for low spin complex, these are species with a smaller number of parallel electron spins. 3D4 will be low spin if the crystal field is strong, but high spin if the field is weak. Then when we talk about high spin complexes, these are species with greater number of parallel electron spin. So for high spin, that means you have more of single orbitals. While for low spin, you have more of paired orbital. That is what we call low spin. They are all in the low energy level. High spin, they will always want to go to the high energy level. So high spin, you have more electrons being singly, but low spin, you have the electrons having smaller number of parallel electrons. So strong field ligands results in low spin configurations. So your D5 will be T2G5, your D6 will be T2G6, your D7 will be this. While for your weak field ligand result in high spin configurations. So your D5, D6, D7. You see for D5, D6, D7, you have, this is for strong field and this is for weak field. For your strong field, you have T2G5. Wide. So here we have 5 unpaired electrons. Here we have 4 unpaired electrons, and here we have 3 unpaired electrons. So let's see how we have D5, D6, and D7. Let's see how many unpaired electrons for weak field. Let's count how we arrived at 5 unpaired electrons. So for D5, T2G, EG, T2G. Please always label your diagrams when you. So for weak field, the field is weak. So we have 1, 2, 3, 4, 5. So here we have 5 unpaired electrons. For strong field, so we have 1, 2, 3, 4, 5. So here we have just 1 unpaired electron, while for this we have 5 unpaired electrons. For this 6, for weak field, we are going to have 1, 2, 3, 4, 5, 6. So we are going to have 1, 2, 3, 4. So this is 4 unpaired electrons. While for this, we are going to have 1, 2, so 1, 1, 2, 3, 4, 5, 6. So here we have 0 unpaired electrons. So that is how we know how many unpaired electrons, if it's 1, if it's 2, if it's 3, if it's 4. So you see for your D5, we had 5 unpaired electrons. For D6, we have 4 unpaired electrons, which we saw. And D7, we are going to have 3 unpaired electrons. So any question? Any question? Do we understand? I've taken time to explain bit by bit because there's going to be question on crystal field energy.
I have a question, ma.
Okay.
For the 7, how do we arrive that it has 3 unpaired electrons?
Okay. For D7, let's see. For D7, For D7, okay, let's see. We'll do it together now. Let's see if we will actually have 3 unpaired electrons. 2, 3, 1, 2. So let's say we are going to do the 2 scenarios, and we are going to do, for this one, it's usually you have 2 scenarios. Here this is small. So we have 1,
You've not used that by brush.
3, 4, 5, 6, 7. So for this we have 1, 2, 3, 4, 5, 6, 7. So we have 1, 2, 3. So T2G, EG, T2G, EG. So for this we have 1 unpaired electron, and for this we have 1, 2, 3. We have 3 unpaired electron for your D7. So you cannot know it. You must know how to. I will remove you from this class now if you don't mute yourself. So whatever configuration you are looking at, you must know how to look at the both scenarios. When you look at both scenarios, then you'll be able to know how many unpaired electrons. So for D7, having a weak field ligand, you are going to have 3 unpaired electrons. But for strong field ligand, because the splitting is high, all of them will first of all pair before they. So here we have 1 unpaired electron, while here we have 3 unpaired electrons. Any other question?
Yes, ma'am.
Okay.
Ma'am, for 3D4 to 3D7 configuration.
Okay.
What's the relationship between the stabilization energy and the pairing energy? Like, how do they affect one another?
How did they? I didn't get. How did they understand what? Because for D4 to D7, how did they affect one another? In what sense? I don't understand.
Like we have the pairing energy and the
Yes.
stabilization energy. That's the delta O something.
Okay.
Like inside now, it mentions that for configuration of 3D1, 2, 3, and 3D8 to 10,
yes,
that there's no
yes,
competition between the delta
yes,
O
yes.
and
For this one, the competition is based on the type of ligand. You know, the type of ligand for your D8, D9, D10 will not affect it, whether it's a strong field ligand or a hair. But for this one, for your, let's say for your D4, D5, D6, D7, there's going to be competition based on the kind of ligand. And the kind of ligand will tell us if it's the delta O splitting is going to be small or the delta O splitting is going to be large. Definitely, even for your D8, D9, the delta O is going to be small or large, but it's not going to affect the number of electrons in the orbitals. But for this one, it's going to affect the number of orbitals in your T2G and your EG. Do I answer the question?
No, ma.
Oh.
Okay, let's say now for 3D4.
Yes.
We have a strong field. That means the delta O is going to be large, right?
Yes.
Now, how will it affect the pairing energy? What will happen to the pairing energy?
They won't be pairing now. We are looking at D4 bar.
Yes.
Okay. We are looking at the 2 scenario B.
No, let's say for strong.
We are looking at the 2 scenario. Am I right?
Okay, yes, let's look at both.
We have to look at both. That is the only way. We have to look at both scenarios. So if this is small, of course the electrons will immediately jump, isn't it? So you have 4 unpaired electrons. Now, if the delta O here is large, the electrons will prefer to be at the T2G level. So we have 1, 2, 3, 4. So there's already pairing here. Because of the kind of ligand you have that gave this a very large splitting. So there's already a pairing.
they are directly proportional. For a large splitting stabilization energy, we have a large pairing energy.
Yes, you have a large pairing energy because the pairing energy here is higher than here. Of course, there's no pairing energy here. So for a high delta O, you have a high pairing energy.
That's
okay. Does that answer your question now?
Another one.
Okay.
Yes, ma. When you were telling us the delta O for the T2G, it's the case here that we have minus 0.4. But when solving in one of the slides, the negative sign is not showing. Is there a reason?
Minus 2/5.
0. Yeah,
minus 0.4. Is it not?
Yes, ma'am.
So I don't understand. What were you saying?
When you were solving for vanadium 2+.
Okay, let's go back there and see. Okay, yes, it's going to be minus. Sorry, there's going to be a negative sign. Minus 2.0 delta O.
The negative sign has to be there.
It has to be there. Yes, the negative sign has to be there.
Okay.
I will include it before I post the slide because it's going to be 2 times minus 0.4. So it's going to be minus 0.8 minus 1.2. Okay. Any other question? So I think I have some questions here. What are the possible configuration of metal ions with the following d-orbital configuration and an octahedral field? What are the possible configurations? So here we are going to have 2 scenarios for each for D4, D5, D6, D7. You can try your hands on that. If it were in class, we would have just done a small quiz, but you can still try your hands on that because of course, you expect questions. There will definitely be questions. Okay, I've even answered it. Let me not put it for you. Try and answer it. Then here I said, draw the crystal field energy and show the placement of the electron for each of the following. So your manganese, this is going to be your manganese 2. This is also going to be your chromium 2 because your water is a neutral ligand. Ammonia is also a neutral ligand. So you are going to determine the splitting, if it's going to be a weak field or it's going to be a low spin. Although I've already given it to you, I'm not supposed to give you. So this is going to be a low spin and this is going to be a high spin. Low spin, that means the delta O is a small. Invariably, it's already telling us that this is a weak field ligand. So it's going to be a low spin. So it's showing that this is a stronger field than water. So that is why it's going to be a high spin complex. So you can, yeah. You said,
when you were talking, you said that you will not necessarily ask us to that the ligands will determine whether it's going to be whether a low spin or high spin. Now that you are now saying that you're not meant to be out.
I gave you a spectrochemical series. I gave you a spectrochemical series, and you have to know the weak field ligand and the strong field ligand. But like here now, I've already told you it's already a low spin, and this is a high spin. I gave you a spectrochemical series. So go and know your spectrochemical series.
Ma'am.
Yes?
I have a question. Based on our previous knowledge, we know that NH3 is a weak ligand.
Yes, compared to water. Look at the spectrochemical series.
My question is this. I think in this question has chromium and NH3. I think we were not given the condition.
Yeah, for this one, Listen now, because water and NH3, both of them are more like weak field ligand. That is why I've already put it here. But in a situation where I don't want to put it, I will make sure there's a distinct difference between water. Maybe here I'll put cyanide, or I'll put a CO, so there will be a clear difference that this is a weak field ligand and this is a strong field ligand. I think that was why I had to put low spin and high spin, because the difference in their splitting is not actually much. Did you get that?
Yes, ma'am.
So if I don't want to do that, I'm going to put a clear difference that you're going to know. Of course, this is a strong field ligand and this is a weak field ligand. Any other question? Okay.
And sometimes our data has minus with it. So my question, that the higher the data, the more negative it is, that means it is lower, right?
The negative is just telling us that the value is for your T2G.
So that means even if it's negative, even if we have 1 is minus 0.8 and 1 is minus 1.2, the one with the higher is minus 1.2 or minus.
I can't even hear anything. The class is loud. I can't hear anything. Okay?
Okay. The question is, let's say we have minus 0.8 and minus 1.2. Which one will be higher? Which one will have the higher data O?
The minus here is just telling you that we are solving for T2G. Your 1.2 will still be higher. Yes, because your T2G is negative, while your EG is positive. So it's just, we are just putting that sign because, yes.
Okay, thank you.
Okay.
My question.
Okay.
You said that means it does more bed of house. You said for low spin that they have more
You said what?
You said for those spin complexes they have more bed orbitals. Why I explain have more single orbitals? So I felt that I spin weak ligand. But from the question, it's kind of confusing.
Which one is confusing?
Because weak ligand, H2 and NH3. We have H2 there to be both spin.
Your manganese, let's look at it. Look at the answer here. You have you have a pairing energy here for your manganese. Why for this you don't have any pairing? You want me to answer the question? Go and answer it. Don't ask me again. Ask me another question. Go and do this. Go and solve this something. Go and solve it. Yes. Don't ask me a question on these two questions I've given you. Ask me another question. Go and try your hands on it. I'm listening.
So ma, please, which because the slides to the lecture,
okay,
like we don't know if it could be uploaded on the LMS today, ma.
I'm going to do that today.
Okay, so like we'll just try and revise before we start the Shribes part.
Yes. I'll put it up today. At least you have all the slides except this.
No, ma.
Okay, don't worry. I will put all the lectures, all my lectures, all the lectures we've had. I've put them lecture by lecture on the elements.
And you're also putting the recorded video too. That's the.
I'll put it. No problem.
Oh, okay. Thank you, ma.
I'll put it. Okay. So See you when I see you.
Thank you, ma.
Okay, bye-bye.
Ma.
Okay, bye. So
Thank
tomorrow.
you, ma. God bless you, ma. Thank you. Bye-bye, ma.
Thank you, ma.
Bye.
Bye, ma.
Bye.
Thank
Ma,
you,
don't forget
Ma.
to.
No, I won't forget.
Again
I'll remind
Yes.
you.
Please do remind me.
All right.